recording this, and let's see what it is. And it is mentioned during this 10 minutes video. Just try to catch it, and after that we will discuss, right? Because since we are going through these mathematical parts, I don't want to talk about this mathematics for the whole complete 1 hour. So that's why I trying to introduce these different concepts, which we will be actually mathematically explained in some of these future lectures, right? And today I'm going to share your YouTube video directly. That's because you can also look at the subtitles as well in case if you can't hear it, right? So let me share this with you. So I assume that, so I have shared the YouTube video here, and I assume that all of you will be able to see it. Right? Let me distribute the frame rate. So let me know if you can.
The concept of space and time is considered to be of fundamental importance to an understanding of the physical universe. We often imagine outer space as the vast emptiness through which planets, stars, galaxies, and other objects travel. And the concept of time feels so natural that we often forget just how peculiar it is. Our current understanding is that both space and time are interwoven in a four-dimensional fabric known as space-time. Thanks to the theory of quantum mechanics, we learned that space is not empty. There are particles rapidly bursting into and out of existence. It wasn't until 17th century that space and time were systematically defined. In 1687, Isaac Newton publishes his Principia, which according to Brian Greene is perhaps the single most important scientific treatise of all time, forever changing our understanding of the universe.
Isaac Newton first articulated a definition on the meaning of space and the meaning of time. And the reason is, when Newton was trying to work out laws of motion, he found something very interesting. He said space is an absolute unchanging arena extending throughout the cosmos, eternal, static. It provides the background stage on which the events of the universe take place. And similarly, he gave a definition for time. Time, according to Newton, is universal. It flows in equal intervals. He used the word equably, from moment to moment, regardless of whether you're on Mars, Venus, another galaxy. Time is ticked off by a universal cosmic clock that's somewhere out there in the universe, relentlessly ticking second after second after second. The equations that followed from that way of thinking about space and time really work. If you use the equations to plot the motions of the planets or the Earth, they really are borne out by your observations. If you use these equations, moreover, in a more terrestrial setting, if you gave Newton a rock and he threw the rock into the air, you could make use of his equations to predict where the rock will land. And indeed, if you do the mathematics correctly, it works. It does predict where the rock will land. In fact, even our space program, even when we go more high-tech, we try to launch a rocket to rendezvous with the moon or any of Mars or the other planets. NASA makes use of the equations that are based on this framework.
Newton founded classical mechanics on the view that space is distinct from body and that time passes uniformly without regard to whether anything happens in the world. Newton's views on space, time, and motion dominated physics from the 17th century until the advent of the theory of relativity in the 20th century. In 1905, Einstein published his theory of special relativity, which showed that space and time were interwoven as a single structure he dubbed space-time.
Einstein was deeply disturbed by Newton's conception of space and time, and it set him out to try to understand space and time more deeply. And he felt that space and time must participate in the universe in a more intricate, a more intertwined, a deeper way, if indeed they were real. So Einstein thought about this for a long time, and by 1915, he cracked it. He realized the role of space and time in the universe, because he realized that they are the medium that communicates the force of gravity.
Albert Einstein revolutionized our understanding of gravity and laid the foundation for the many scientific and technological breakthroughs that came after him. In November of 1915, Einstein made one of the most profound intellectual breakthroughs in the history of physics when he developed the full implications of his ideas on gravitation into his general theory of relativity. Departing from Isaac Newton's conception of gravity as a force transmitted instantaneously over distances, Einstein positioned that gravity operated as less of a force and more of a field which distorted space and time around massive objects. Thanks to Einstein's general relativity theory, we can describe gravity by attributing it to the curvature of space-time that occurs in the presence of massive bodies. The stronger the gravity, the more space-time curves, and the slower time itself proceeds. Time goes faster the farther away you are from the Earth's surface compared to the time on the surface of the Earth. This effect is known as gravitational time dilation. For example, if you climb on top of a skyscraper, time passes nanoseconds faster for you than for someone on the ground. Now, because the effect is so small, you will never notice the time difference. However, the time dilation due to Earth's gravity is significant enough that it makes, for example, GPS satellites adjust their internal clocks to pinpoint the location of the receiver in the ground. The accuracy of GPS positioning depends on precision in time measurements of billionths of a second. To achieve such timing precision, however, relativity must be considered. Special relativity shows that if we place a clock on a satellite and compare its recorded time to an identical clock in our rest frame on Earth, the satellite's clock will appear to be running behind. For GPS satellites, this difference amounts to about 7 microseconds per day. On the other hand, general relativity shows that those same clocks will tick 45 microseconds per day faster. The combined effect of relativity is that the satellite's clocks tick faster by about 38 microseconds each day. That sounds like a tiny amount. What difference could that make? Well, unless these relativistic effects are accounted for, the errors would accumulate at about 10 kilometers per day. And that new restaurant you wanted to try, it would not be anywhere near where the GPS thought it should be. These effects would be far greater if you are traveling at close to the speed of light, or if you happen to find yourself in an area of extreme gravity such as a black hole. A black hole is a region of space-time where gravity is so strong that nothing, no particles or even electromagnetic radiation such as light, can escape from it.
If space is real, and if it can respond just the way any more familiar object can be affected and respond, then it is subject, space is subject to the laws of the universe, in particular a body of law known as quantum physics. And when you apply quantum physics to the fabric of space, you run into some very deep problems.
To describe the gravitational field of a black hole and the physical quantities such as the space-time curvature which diverge at the center of the black hole, we need a theory that goes beyond general relativity into the quantum mechanics. Such a theory should allow the description to be extended closer to the center and might even allow an understanding of physics at the center of a black hole. No theory has yet proven successful in describing the general situation where the dynamics of matter, molded with quantum mechanics, affect the curvature of space-time. A conceptual difficulty in combining quantum mechanics with general relativity arises from the contrasting role of time within these two frameworks, because, in quantum theories, time acts as an independent background through which states evolve. As a particle travels, it explores every possible path, and what we observe is a melding of them all. There are many proposed theories that attempt to explain what gravity is. String theory and loop quantum gravity are the most popular among these theories.
When we do our analysis, like when we do our quantum mechanical analysis, We typically focus on analyzing the properties of a small number of particles. Or if we're talking about universes, we model the universe as a very homogeneous structure so that we don't have to analyze all of the intricate details, simply because we can't, at our current level of understanding, do that. So that's where we've gotten in our search to understand the deep laws. All of these ideas are emerging from us following in the tradition laid down by the greats, by Newton, by Maxwell, by Einstein, where they showed us that mathematical calculations can be a potent guide, a sure-footed guide, a gateway, if you will, into realms that we have not yet been able to probe experimentally.
Right, so I guess I will stop it from here. And I will also upload this same video to the LMS. The previous video has already uploaded to the LMS as well. So if you have an issue with the data problem or anything like that, you can watch the video at the LMS. But if anybody needs the link in the YouTube, I can send that as well. And the other thing is the scientists who talk in these videos, in here it's Professor Brian Greene, who is one of the famous astrophysicists in Columbia, I guess in Columbia University in USA. Right? So these, all these informations are kind of reliable in that sense, so you don't need to worry about anything. And Naveen, do you have a question to ask? Or?
No, sir.
Right. Okay. So okay. Right. And so one thing actually I want to emphasize, one of the important things that have two things that I can discuss with you that emerge from this video. Number one is about the Newton's gravitational laws. Even though we are learning about this general theory of relativity, still you can apply the Newton's gravitational law for most of the things that we come across in day-to-day life, including these calculations that used by NASA for these space missions, right? Still they are valid. But there are certain situations that this application of general relativity is very, very important, right? I mean, it is true that it is very important in the field of astrophysics, like calculating different phenomena around the black holes and these massive galaxies and around galaxy clusters, those kind of things. Apart from that, there is one thing that is which is very applicable for us in these days, right? Did anybody notice what is that? Anybody can answer for that? What is the application of the general relativity that is talked in this video? If anybody listen carefully, can anyone tell what is that? Yeah, so I think I got one message. How about the others? Naveen, Nimmi, Miller, Taranga. Anybody have any idea if you could look at the video? What was that application? So nobody knows it except Sajini. Right, so I think it should be in satellites, right? Yes, it's something related to the satellite, so that is true. What exactly is it about? So if I tell it in a very short way, that's about your Google Maps, right? now everyone is using GPS these days, right? And all of you know that this Google map that you have in your phone that applies, that works according to these GPS satellites, and there are around 20 IS-12 GPS satellites around the Earth that helps locate these positions, right? Yes, I mean that's GPS. So thank you for all of your answers. And I guess that you probably have understood how important the calculations that we do for the curvature of this space-time for these GPS calculations, right? Now this the GPS, we call this the set of satellites as the GPS satellite constellation, which has around 24 satellites, right? They are arranged in 6 equally spaced orbits, if I remember it correctly. And the important thing here is due to this curvature of the space-time, the time ticks in 2 different ways on Earth and on this GPS satellites, right? So what happens is, as a result of the effect of the special theory of relativity, the time ticks around 7 microseconds, or 7 years. It should be let me check it. I guess this should be yes, 7 microseconds slower than you expected. And on the other hand, due to the curvature of the space-time, which comes as an effect of the general relativity, the time goes faster than compared to Earth. That the difference is 45 microseconds per day, right? Now you can see that these two effects work in 2 different ways. According to the special theory of relativity, due to the orbital speeds that they have for these satellites, because the satellites has orbital speeds around 14,000 kilometers per hour, and due to that effect, the clocks are slowed down by 7 microseconds per day. You can see it's a very small amount, right? And the other thing is, because these clocks are around 20,000 kilometers above the Earth, so they, as a result of that, the gravity is weaker, right? Around 4 times weaker than the gravity on the ground, right? Because of that, the clocks on these satellites are moving 45 microseconds faster compared to the Earth, right? And because of that, if you take the difference, there is a difference of around 45 minus 7, that will be 38 microseconds, right? Now this 38 microsecond difference is affecting for our GPS locations. And how much it is affecting, if you look at the video again, for each day, there will be a 10 kilometer difference if you did not take these calculations and make the corrections in these clocks inside these satellites, right? So you have to automatically adjust these clocks on the satellite to get the correct position. And what happens is, if you do not do it, there will be around 10 kilometers difference in your location for 1 day, right? So think that if for some reason these clocks stops for working for 1 day, that will enough to affect the whole world, right? So we don't think about this, but this is one of the very nice applications of the Einstein's theory of relativity. So otherwise, sometimes most of us think that there is no use of these theories in our day-to-day life, right? Now you can see that how important it is, and especially on these days, if you look at order, or if you try to locate someone's home or a restaurant, something like that from the GPS, I guess you are probably using it more than us. You can see that what happens. You will never find the restaurant in your location if one of these clocks gets stopped 1 day, right? Just for even like a change or malfunctioning of one of these clocks for few hours will be enough to make this effect on our day-to-day life, right? So this is why it is very important that you apply these corrections precisely, right? Right. So that's one of the things that I need to talk with you before I go into these mathematical theories behind this. Now, as usual, let me open up this second section that we have to talk. So remember that we are just formulating this theory of general relativity. Right, so let me share this here. So I think we talked about the first section, how to write the metric and how can you write it, how to get the inverse and those kind of things, right? And different applications. And also about the index notation. Under that, we have talked about the Einstein summation convention and how that works, and yes, different applications, those kind of things, right? Now, I hope all of you can see my screen. So for today's lecture, let me briefly talk about this concept about the manifold. And I mean, again, if you have done, double maths, you probably know about these things. But for those who haven't done, I just need to mention some details about this concept, which is one of the important things that you have to learn when you try to understand about this theory of general relativity, right? Now, to start with, if you consider this Einstein's theory of general relativity, when he tried to formulate it, there were two important things that he has considered. The first one is matter and energy curve, the space-time. I think we have discussed this last Monday as well. And the second one is space-time can be modeled using mathematical structure known as a pseudo-Riemannian manifold, right? So that's just a word that you use. And in this next few slides, I will show you what is a manifold, right? And this gravitational force, as you saw in this video as well, in general relativity becomes a property of geometry of space-time. So that's what happens. So we don't consider gravity as a force anymore in general relativity. So we consider that as a property of the geometry of the space-time, right? Right, so let's look at the next one, the geometry of the curved space-time. Now let's consider the ant. So I have a small handwritten hand-drawn picture right at the bottom just to make sure that you understand what I mean here. Consider an ant crawling over a skin of an apple, right? So that means there is an ant. So let's say this small dot right here, try to move on this surface of an apple, right? So everybody knows an apple, right? And even though the ant determining to walk in a straight line, it will drawn into the dimple where the base of the stalk is. So that's so there is a small spelling mistake here. I will do that correction. So ant is determined to walk in a straight line, right? But what will happen eventually is, even though the ant needs to walk on a straight line, it has to walk on the surface of this apple, right? And we all know that apple is a curved surface, right? And because of that, so it will automatically be drawn into this position right here, which we call as the dimple, right? Now ants, basically what has happened is, even though ants need to move on a straight line, the ant's path is determined by the curvature or the geometry of the surface of the apple, right? So you know that an apple has a unique geometry, right, which is closely in very close to the spherical shape, and the path of this ant is basically determined by that curvature or the geometry of the surface of the apple, right? Not by the ant itself. Right? Ant wants to go in a straight line, but it cannot do it itself, right? Because it is the geometry of the surface that decide the path of the ant, right? So that's what you need to understand here. Now, if you consider a flat space, this is not an issue. In a flat space, you know, you can move in a straight line, right, without any issue, right? And so what this teaches us is in the vicinity of massive objects, when you have like, I mean, this is just an example, but if you look at a very massive objects like the planets and stars, this space-time is curved, right? And as a result of that, if you consider a free particle, including light, they will not be able to move in straight lines, right? Which is pretty much similar to what happens to ant on this apple, right? And instead, what will happen is you have to follow this straightest possible path dictated by the geometry of the curved space-time. So, which means you can follow not the straight line, but the straightest possible path, which is dictated normally, which is controlled by the geometry of the curved space-time, which is pretty much similar to this curved apple, right? Once again, it's ant need to go in a straight line, but cannot do it itself, right? Because its path is completely governed by the geometry of the apple itself, right? Now, this on a curved space, this straightest possible path has a specific name, and that name is called geodesic, right? And there is an equation that we will derive later, which we call as a geodesic equation, that gives you the straightest possible path on a curved surface, right? So we will go through one or two examples for that as well. Right. Now, to describe this curved space mathematically, we need to have some kind of concept, right? Now we got the idea what happens actually, but when you need to explain it mathematically, you know, when you have something, you have to explain it mathematically, right? That's how physics works. In the same way, when you need to describe this curved space mathematically, we use this concept called manifold, right? So that's what I want to introduce today. And a manifold is normally we used to tell that a smoothly curved space that is locally flat, right? A smoothly curved space, but if you get a small area, that area may look flat. So that's the idea, right? Now, if you look at examples, a circle is a 1D manifold. And if you look at a surface of a sphere, that is a 2D manifold, right? So that's a 2-dimensional, right? Surface of a sphere. So if you look at a small piece of the surface of the sphere, it looks flat, right? So that's why it's a curved, a smoothly curved space. And locally, if you get a small area, that particular area looks flat, right? So that's the idea. And these kind of surfaces we used to call as a manifold, right? Let me. Now, if you now relate this to 4-dimensional space-time, if you look at space-time, the 4-dimensional space-time is a manifold. We used to tell that as a manifold that is locally flat, right? And the flat surface of special relativity, I guess all of you are familiar with special relativity, right? If you look at the flat surface of the special relativity, these kind of flat surfaces can be found in deep space. That means far from the influence of the gravitational field, because when you have gravity, it curves the space-time, right? So, but if you can find if you can go to the deep space, where you can avoid the influence of gravitational field, then you can have these kind of flat spaces, right? Which you have already talked in a special theory of relativity, right? And in a flat space, as I told you before, these free particles can move in straight lines, and in the vicinity of massive objects, space-time is curved again. Right, now we know we have a rough idea about the manifold. Now let's look at what we mean by Riemannian manifold, right? Right. Now, in order to model the space-time in general relativity, a manifold must have or must satisfy two properties or two conditions. And the first one is called the manifold should be differentiable. And the second one is called, it should endowed with a symmetric metric tensor, right? Now the symmetric tensors we will learn under the section about the tensors, but here the idea is, let's take, you have a metric called G mu nu, and if you can interchange the indices like G nu mu, both should be equal to each other, right? And there are certain times that you get G mu nu equal minus G nu mu. So those are called antisymmetric. But to be a Riemannian manifold, it should be a symmetric metric tensor, right? I mean, you will get to understand some of these once you do this mathematics. Now, when you have a manifold with about two properties, so they are also known as Riemannian manifold. So that's how this name called Riemannian manifold came. Actually, this the name came from a German mathematician called Bernhard Riemann, who discovers the metric that contain all the information to describe the curvature of a manifold, right? Now, if you look at if you need to describe the curvature of a manifold, which is, I guess you know what is a manifold is. It's a curved surface that is locally flat. And if you need to describe that curvature in a mathematical way, so that way of describing is actually discovered by this mathematician, right? And actually we call that as Riemann curvature tensor, which is one of the important tensors in general theory of relativity, and we will learn about that. And basically, if we know the metric of a particular certain thing, then we know the manifold, right? So that's the idea, right? Now, as an example, if you think about an n-dimensional Riemannian manifold that has a line element, we can write it in this way: dl squared gij dxi dxj, right? Now where dxi and dxj are coordinate differentials and gij is the metric, right? Now remember, I am using here the Einstein summation convention here. Now you can see that gij, and then you have I and j here again, which means this is an expression that I need to sum over, right? So these are like dummy indices that you have to use to sum this expression. And this is now in Minkowski space, which is the space that you have used for this special theory of relativity. You can write ds squared equals c squared dt squared minus dx squared minus dy squared and minus dc squared. And this metric related to this particular expression can be written in this form, right? And I guess you probably have seen this in a theory of, under the theory of special theory of relativity, right? So you have a diagonal metric. The first element is 1, and then you have minus values. So that's why you get 3 minus signs here and the plus sign here. And I guess in this particular metric, I have assumed that the value of c is equal to 1. And if you combine this expression and this expression, and then you can understand how I have wrote this expression for dl squared, right? So the first one, you get the metric element is 1, so gij will be 1. and this will be dx1 and dx1. So that's how you get, sorry, dt and dt, the same expression, that will be dt squared, and then you get the metric element as minus, so that's why you get minus, and then the metric element gij is equal to my 1 right here, and then minus 1 times dx and dx again, right? Because you have the same indices here, dx1 and dx2 and dx2, whatever, right? Then you get the second element. So that's how you write, right? Now, even without telling about this expression, you will see that sometimes I use only this expression right here, and you have to understand it from the previous lecture, right? So that lecture is about how to use this Einstein's summation convention, right? So that's why you need to follow this notes carefully and in an order, right? Because you cannot just jump into one position and understand it. So make sure that you follow it from the beginning. Right now, if you have diagonal elements which are equal to plus or minus 1, then it will be a flat space. So that is the space that you have learned under special theory of relativity, right? And then if the coefficients does not equal to plus or minus 1 for a particular coordinate system, the next question is, how do we tell whether the metric defines a flat space? Right? Because if it is plus or minus 1, then it is clear. Right, now here is the way how we define whether a particular space is flat or not, and that is defined by basically the Riemannian curvature tensor, right? Once again, I can see that there are a few spelling mistakes here. I will make those corrections when I upload the newer version of that. So the way that you decide whether a particular space is a flat space or not is based on this particular expression, which we called as the Riemannian curvature tensor. Right? The idea is, if the value of the Riemann curvature tensor is equal to 0, it is a flat space. And if this Riemannian curvature tensor does not equal to 0, it is not a flat space. Right? So that is how you decide whether a particular space is a flat space or not. And I have mentioned it in terms of word here, if R, L, I, J, K, and this is, by the way, this is a tensor, right? And we will remember that we will learn about basic properties about the tensors in one of the coming lectures. We have not come up to that point, but just to introduce you how you can tell whether a particular space is flat or curved, I have to tell you here that you need to use the Riemannian curvature tensor. Right? So that's how you decide it, and this is why we will learn about tensors. And these are actually, there are lots of things that you may not understand right now here. Even in the right hand side, there are partial differentiations of different terms, and these are actually called Christopher symbols or connection coefficients. We will learn about those as well. And for the time being, just understand that this is a tensor, and this is in fact a fourth rank tensor. We will learn about those as well. And depending on the value of this tensor, you can tell whether a particular surface is flat or not, right? So that is whether a particular surface is curved or not. That is the idea. Right. Now, apart from that, you may have a doubt that how you actually decide about this curvature, because this can be, defined in few different ways. In relativity, in general relativity, we are actually concerned about something called intrinsic curvature of an object or a surface. Now, there are two types of curvatures. One type is called extrinsic curvature, and the other one is called intrinsic curvature. Now, if you take a cylinder, which is made by a rolling of a piece of paper, it has an extrinsic curvature compared to flat table, right? So that means it externally it looks like curved. But what happens if you actually, if you look at the same cylinder intrinsically, this cylinder is actually flat. The idea is if you unroll and unroll the whole cylinder, you can clearly see the surface is like rectangular in rectangular shape, right? So that is the idea. So which means it's actually flat surface if you look at intrinsically, but extrinsically it looks like a curved surface, right? And so I hope from that example you can understand what an extrinsic curvature means, what an intrinsic curvature means, right? And if you look at a ball on a table, if you think about a ball that is kept on a table, that is also extrinsically curved space, right? Externally, it looks like a curve. And the ball's surface is also intrinsically flat, right? Now, if you look at a sphere, just think about a sphere. The two lines that start parallel at the equator. Equator means just think about our own, celestial sphere, right? They will meet at the poles, right? If you remember these right accession and declination lines on our latitude and longitude lines on our universe. So on our Earth, you probably remember that there are two lines that start parallelly from the equator, but they end up, finishing at the poles, right? So which means the two lines that start parallelly, but they will end up at the poles, which means they cannot, they will meet at one point. They cannot go like parallel lines, right? That's because of the curvature that you have. And so the sphere, unlike the cylinder, the sphere cannot be flattened without any distortions, right? So you cannot make it flat without any distortions, right? Now this is the problem that you probably have seen this when you need to make the world map, and if you need to make it a two-dimensional flat surface, it is not easy. Now for the general relativity, we are only interested in intrinsic curvatures, right? Like the last one that we taught. Right, so let me take a surface of a sphere, right? Now, one of the simple examples that you can look at as a 2D manifold. Now, so I actually made this as a question for you. Write down the line element for a 2D sphere in polar coordinates. And since, you do not have time and I cannot see a way that I can get the feedback from you, I will just discuss this with you, but try to do it yourself, right? Now, especially when we are doing this online teaching, it is hard to get the feedback from you. But so the responsibility is you to do this yourself and try to understand, right? Especially these mathematical things, I cannot ask you to even write it in the chat box sometimes because these are like matrices. And so if you have a 2D sphere, the line element you can write, I think we discussed this last Monday as well. If you take the line element dl squared, that will be equal to r squared d theta squared and r squared sine squared theta d phi squared. And you cannot have the last term, which is dr term, because now when you think about a sphere, the radius is constant, right? So that means the dr should be equal to 0. Now, once you have this line element, you can write down the metric for this surface, and we have done this before as well. The metric will be this one right here. You need to get the theta term, theta phi term, and phi theta term, and phi term. And from this expression, you can see that you only have the diagonal elements, right? You have the theta term and phi term. So those are the two terms that you have. So which means you will end up having these diagonal element, and the anti-diagonal element of the other two elements should be 0, right? So this is the metric for this surface. And the next one is write down the inverse metric, right? The inverse metric is, be careful with the notation. This notation, you have the G lower ij, and when you change it to the inverse metric, you write it as G, then subscripted ing, right? Since you only have the diagonal elements, you just need to take the reciprocal of each element, which will give you the inverse metric, right? Right. Now let's look at an example. Keep that in mind. Let's look at an example. Find the circumference C of a circle generated by sweeping a point at a constant angle theta around the North Pole on the surface of a sphere with radius r, right? Now, rather than me doing it, so here is the diagram, right? So I would like all of you work on this problem and come up with an answer, right? And this is actually already posted in your note, but I mean, I would like that you do it from your hand and send it to me as an assignment, right? So this will be the first assignment I would like to have from you, and this should not take more than half an hour, so that you can submit it by Friday, right? Now, this is an example that will take into everything that you have learned up to now. And here is this diagram actually explains basically what you have to do. You have to find this circumference right here. Find the circumference of this circle generated by sweeping a point at a constant angle theta. Here is the constant angle. So you need to find this circumference, right? So there is a little bit mathematics that you have to do from the knowledge that you have up to now. First, try to do it yourself. And second, just go through the note. I have done it myself. You can refer that, but make sure that you understand what's going on and find the solution, right? And submit it as an assignment, which I will be creating now. Just submit it, and from there on, I will start the next lecture, right? Anybody have any questions up to here?